Okay, so let's talk about absolutely convergent, conditionally convergent, and divergent. Okay, so if I'm going to discuss something being absolutely convergent, here's what that means. It means that the absolute value of the series and the series itself are convergent. Okay, so there's a couple of different things that you have to test there. You have to test the absolute value of the series, and then you have to test the series itself, and we're going to go over that. Now, we can have what we call conditionally convergent. Okay, and that means the series is convergent, the series itself, but the absolute value of the series does not converge. Okay, and then of course, if something is divergent, we know that neither the absolute value or the series converges. Okay, and here's an easier way to look at that. All right, because that's a whole, it gets a little kind of confusing with the absolutely and conditionally. So if the summation of the absolute value of the series is convergent, so we start off testing the absolute value of the series. If it's actually convergent, then the series itself will be convergent, and we say absolutely convergent. Okay. Now, if the absolute value of the series diverges, that doesn't mean the whole series is divergent. That just means it's not absolutely convergent. It could still be conditionally convergent. So, if the summation of the absolute value of the series is divergent and we get the summation of the actual series itself is convergent, and this is called conditionally convergent, I'm sorry. Okay, so the absolute value can diverge and the series itself still converge, and it's going to be conditionally convergent. Okay, if the absolute value of the series, if the sum of the absolute value of the series is divergent and the series itself is divergent, then we say the whole series is divergent. Okay. Now, so let's look at an example. Okay, let's say I have the summation of n equals 1 to infinity, and this is a little bit like one of the problems that you had on your homework of cosine n pi all over n cubed. Okay, so the first thing I'm going to do, I'm just going to write a few things out. So if I put in 1, I get the cosine of pi. Well, that's -1 over 1 cubed is 1. Okay, and I'll go ahead and write that there so you can see. Plus, okay, so I'm going to put in 2. Cosine of 2 pi is 1 over 2 cubed. I don't have to work that out. All right. Then if I put in 3, well, the cosine of 3 pi is -1, so -1 over 3 cubed. And you get where this is going. Okay, so it is an alternating series in itself, but I'm not real worried about that right now on this particular one. Okay, so I'm going to now check on it being absolutely convergent, because if it's absolutely convergent, if that absolute value portion is convergent, then the series itself is going to converge, and I can say absolutely convergent. Okay, so I'm going to I know that if I take the absolute value of this, what's going to happen? What do I wind up getting? I wind up getting a positive 1 over 1 cubed, right? Everything comes out positive, plus 1 over 2 cubed, plus 1 over 3 cubed, plus 1 over 4 cubed. Well, that really looks like what? It looks like a p-series, doesn't it? What does that p-series look like? It looks like the summation of n equals 1 to infinity of 1 over n cubed, right? That's going to produce the same thing. Well, it is the same thing as the p-series. When I take the absolute value of it, it's acting like the p-series 1 over n cubed. Well, then what is p here? P equals 3. Since p is greater than 1, the absolute value of the series converges. Since the absolute value of the series converges, what can we say? We can say that this particular series is absolutely convergent. Okay, and that should be by the absolute convergence theorem. You can look that up. But by the absolute convergence theorem, the original series also converges, making the original series absolutely convergent. Okay, let's look at another one. What if I have the summation of n equals 1 to infinity of -1 to the n plus 1 all over the cubed root of n? So let's write out what this looks like to start with. I'm going to write out a few of the terms in the series. If I put 1 in there, I get -1 squared, which gives me 1 over the cube root of 1. I'm going to leave it like that. Plus, well, let's wait on the plus, because if I put 2 in there, I get -1 cubed, which gives me -1 over the cube root of 2. Okay, then I'm going to get plus, because when I plug in 3, it becomes to the 4th, 1 over the cube root of 3. Okay, so we see that alternating right there. So let's take the absolute value of that, because that's what I'm going to check for first, is absolute convergence. Okay, so I've got the sum of n equals 1 to infinity of the absolute value of -1 to the n plus 1 all over the cube root of n. Well, what does that do? That really becomes 1 over the cube root of 1 plus 1 over the cube root of 2 plus 1 over the cube root of 3. Okay, well, what does that look like? That really looks like the summation of n equals 1 to infinity looks like a p-series, guys, which is 1 over the cube root of n. Okay, that's fine. We can take that. We can see what that is. This is a p-series. Let's change that radical back into an exponent. So this is really the summation of n equals 1 to infinity of 1 over n to the 1/3. What is p here? P is 1/3. P equals 1/3, which is less than or equal to 1, meaning the absolute value of the series diverges. Okay? Well, that's fine, but that just tells me it's not absolutely divergent. It could be conditionally convergent. Okay? So we need to now, in order to see if it's conditionally convergent, actually determine if the series itself is convergent. Well, what was the series itself? Well, the series itself was n equals 1 to infinity of -1 to the n plus 1 over the cube root of n. Okay, this is an alternating series, so we can use the alternating series test. Okay, I'm going to say alternating series right here because I've got that -1, making it flop back and forth. Remember, there's two criteria in order to prove if it is convergent or divergent when it's an alternating series test. The first thing we need to do is identify a to the nth, which in this case is going to be 1 over the cube root of n. I'm going to take the limit of that. That's step 1. Let's see if I can fit it in here. And I'm going to ask myself the limit. What does the limit as n approaches infinity of 1 over the cube root of n? What does that go to? Well, as n gets bigger and bigger, I take the cube root, I'm going to get a bigger and bigger number. Okay, so that actually goes to 0. So it does meet that criteria. And what's my second criteria? My second criteria says that a sub n plus 1 has to be less than or equal to a sub n. Okay, which means 1 over the cube root of n plus 1 has to be less than or equal to 1 over the cube root of n. Is that going to be true? Well, yes. Okay, because that n plus 1, even though I'm taking the cube root of it, produces a bigger quantity than just the cube root of n. It's in the denominator. The numerator is 1, which means that value of 1 over the cube root of n plus 1 will be smaller than 1 over the cube root of n. So that works out. So that tells me that this function is actually, not function, this series, I'm sorry, is actually conditionally convergent. Okay. And that's a little short blurb over how I tell if something is absolutely convergent or conditionally convergent. Because I noticed on the homework, there were some that you would just put convergent. You wouldn't tell me if it was absolutely or conditionally. And that was kind of the point of the exercise on that. So that's a little practice right there, a little review over how to determine if something is absolutely or conditionally convergent.